Its name is IBM Flash System 9100. So we are part of the development team. I am joined with my colleague Mohit. So like what we are going to present you is like Flash System 9100 used to have, is having NVMe drives, but it was not having support of host side. NVMe thing was not supported. So what we did last year we developed the code for NVMe-FC host support, and Mohit did the testing of it, and he did performance testing of our initial software, and we would like to share the figures with you. So like this is, we want to present in this session. Yeah, so what is the agenda of this session? So basically like I have told you that the Flash System 9100 is having NVMe SSDs, but not the host side support of NVMe-FC protocol. So first of all, I want to tell you why NVMe, why not SATA or SAS drives, why NVMe SSD, why we have extended NVMe to NVMe-FC, then a little bit of deep dive implementation, how we did that, then the performance finding that Mohit did, we would want to like to share with you. The special thing about this is we are wearing the workload when we did the performance, and we have a very big graph like depending upon lot of queue depth, how the performance is there. So like we would like to share with you, and also how customer will benefit from this. Now the third point we would like to make is the benefits that we will get out of those performance. So we would like to measure these into what customer workloads will be able to take benefit out of it. So this is all the agenda of this session. So a lot of things have been, told about the storage and history and evolution. So like if we just start with, like for example, HDD, right? Like it is told in many sessions earlier also. So HDDs were things of 1980s, right? Earlier we used to have very big storage, having few MB of data and few MB of transfer rate. At that 1980s time, in 1986, SCSI was, standardized. And like earlier, we used to have PATA drives, like these are famous drives that you would also be knowing. So we had something called PATA. And after that, it has some, disadvantage, it has some restriction. Then came the SATA. Then again to improve that, the thing came SAS. So the thing is, the storage things we are keep on improving. Improving in the sense it should have more IOPs, it should have more bandwidth, it should have less latency. So like all these things are evolving, and we had, a presentation from Intel, from Samsung, like they are developing device which have those, attributes. Now, when we talk about SAS and SATA, so like these were the technologies that were legacy. For example, SATA, before it was PATA, and it, superseded, and then SATA came. Then a new technology, SAS, came, which was based on SCSI, and then it came. And, scaling out, lot of, devices can be connected. But again, the thing was the throughput. If you can see that it was limited by 1.2 gigabyte per second, because the SAS controller which was attached to it was not able to, put more, IOs to it. And it was having, larger latency and higher host CPU utilization. Now, the next thing which came was PCI attached SSDs. So when we talk about PCI attached SSD, we know that, the throughput that is generated by PCI Express, like we have, Gen 3, Gen 4, a number of lanes like cross 4, cross 16. So these interface can deliver more throughput, and, we can, process lot of data there. So earlier what happened, like when these PCI flash thing was established, it was not standardized. Like each vendor developed its own drive and it attached to it, and they told that they are getting better performance with respect to SAS and SSDs. So like this was creating some trouble, like there was no unique standardization of the devices. Every vendor was, making its own devices, and they were not compatible with all the operating system and all, because there was no standard as such. Now later what it came, NVMe standard was developed for these drives. So like lot of companies collaborated and they devised standard for NVMe SSDs. So the major thing is, like these NVMe SSDs, they have lot of queues. So when we talk about SATA and SAS, it was only having one queue, and at a time 32 commands, 64 commands, or 256 commands were there. But when we talk about NVMe, the theoretical limit is 64,000 queues, and in each queue 64,000 commands can be there. So you can see the difference between the architecture that is made from the very scratch, how efficient it is. So as I mentioned that this was standardization of PCI flash technology, and there were drive limitation, how many can be attached. So like we were having good number of IOPs, good number of throughputs, and very lower latency and lower host CPU utilization. Now as I was talking about, our product had NVMe drives, but the host was sending SCSI IOs, right? Now when we are going to do NVMe host attach, what it will benefit. So there will be lot of drives which can be shared among lot of hosts. So like this is one of the advantage. Earlier, these drives were local to the host, but now these drives are across the SAN, and lot of hosts can utilize these SSDs. So this is the advantage of it. So lot of queue depth are there. So I will continue with this in my next slide also. Okay, so on the left-hand side, you are seeing that this is a host interface with NVMe SSD drives, attached to it. Now we are shifting it to NVMe backend, NVMe over Fabric. So we have attached a Fabric. There is a device driver. There is an application. So earlier, like what was happening, this SCSI thing was bottlenecking it. NVMe SSDs were having, very good bandwidth and IOPS figure, everything. But there was, when SCSI is there, then that will create a bottleneck. So what we have done, we have extended this. So this NVMe SSDs, how do they work? Like they work on queues, and queues are dispersed across various cores. And parallel thing can be written to NVMe. So like when we talk about HDDs, right? So HDDs used to have this mechanical drive, and the protocol was written in such a way. But these NVMe SSD drives have the capability to have parallel IOs, and these IOs can come through lot of queues, which I have told 64,000 queues and 64,000 commands. So what we are going to do is to extend this queue thing till the application level. So this application will create request and negotiate for queues, and will do login, and things will be available to the application. I will talk more about it in my next slide also. So, so like this is how we are extending to NVMe Fabric. Now, okay, yeah, sure. So I would like to take this question first. so like this is this is a setup where we have SCSI host, and this is all flash array, and SCSI-FCP was there. So as I have already told you that, suppose this is not supporting NVMe right now, and you are asking for how much more cost will be required to upgrade it to NVMe supported SAN, right? So the thing is, if earlier you were having a generation 6 adapter which can support NVMe in future, for example, like most of the Gen 6 adapters have the capability, you just have to upgrade it from the host side, upgrade it from the target side. That's it. No more cost is required, zero cost, if I say, for using existing things. So like this is also having generation 6 adapter, and this is also having generation 6 adapter. So what will happen is, the same port which was doing SCSI IO, it will do the NVMe IOs, and the same switch port, like it will do the NVMe IO over the all-flash array. And if you want to add a new NVMe-FC host, like you could have used, any previous version host having generation 6 adapter, you can add a new one. Like if you buy a new one, you can add, but you can use that thing also, like your existing one. And this SCSI host was already there. So the thing is, like this is something which can customer, use it right from the day one. So like we deliver it, and you know that most of the data center we have today have FC adapters in enterprise market. So like we will have lot of customers there because they don't have to do anything. And fiber channel is something like the expertise is known to them. And when we give NVMe, not much is required. So let me, come into some more implementation detail of the deployment. So earlier what was happening, there were some LUNs or volumes which were mapped to NVMe-FC host. So admin knew what it has to do. Suppose it has 4 ports. The 4 ports will be having 4 WWPNs. Suppose this is also adapter generation 6 adapter. This will be having 4 adapters. So what you have to do is, this is a SAN switch. You just have to zone those WWPNs. And the SCSI IO will come, they will inquiry, and the LUN will be exported to it. Now, we have, talked about the capital investment. I want to talk about the capital investment in terms of admin also. Like, will require to hire more number of people with new expertise? No. Because the NVMe will travel through FC protocol only. Earlier, FC protocol was having SCSI. Now, it will send NVMe commands. So the admin aspect of it is, this whole thing, NVMe host, will be denoted by something called NQN, name qualified name. So NQN qualified name. So this thing is also there, similar to IQNs, which we have in iSCSI. So when you see this operating system, it will have something called NQN, and this will have some target NQN thing. So this needs to only discover, like it will do a query, it will say, what is the name of its IO subsystem? It will get that this is the name of my IO subsystem. It will do a login. By login, like we mean, in terms of commands, this is called association. When this association is accepted, then on the top of this association, we create lot of queues. I will, talk this in my previous slide also, I will when I get back. So lot of queues are created, and all those queues are, set some limit, how many commands can at max be there. So the important thing is, like when we do a negotiation and when, we say that only this much command can be done, so this is a mechanism of flow control also. Like we know about B2B credit and all, how efficient is fiber channel. On the top of it, we are restricting initiator not to send the command that we cannot handle. So like these are also the admin steps. The other thing is, I have talked about this physical connection, right? I have talked about this physical connection, but the thing can be, you want to totally, segregate your NVMe connection and SCSI connection also. How you can do this, I'll tell you. I have already told that FC was having, WWPNs here and WWPNs, and the logical connection was established. Now what we can do as an improvement is, suppose we add a new WWPN, which is a NPIV ports, right? So when we talk about this NPIV ports, a new logical connection will be established, and we will not interfere with each other, with SCSI and NVMe. So like this is also some improvement that admin can do. So like this was, how easy the NVMe-FC deployment is. Now let's move to the previous slide. Okay. So we have talked about, in breadth about NVMe, SSDs, and NVMe drives. So the protocol, is the base protocol which supports those drives. So we have, NVMe IO command support for read write, NVMe admin commands for, controlling the attributes, and we have multipath and reservation, all these stuffs which belong to NVMe SSD stuff. Now to extend this, we have this concept of fabric command support and discovery support. So, so to tell you, discovery support, like what is a discovery support? So like in terms of if I talk about fiber channel protocol, how does the fiber channel protocols comes to know like what other thing it can see, and what other thing it can discover, is basically like these fiber channel ports are zoned in switch, right? You do a query command like for example gidft in the switch, and it will tell all the all the ports which are visible to it. Similar to that, so like in discovery support, what we have done is, in discovery support, there is a NVMe initiator. It will query to a very well-known address, and it will say, what are the all IO subsystems that I can see? So these IO subsystems will be, replied back from the target side, and after that, it will tell what are the volumes can be exposed to the host. In NVMe terminology, volumes are known as namespaces. So there is a difference between the terminology that SCSI uses and what NVMe uses. One of the other differences is, like the SCSI protocol, when it maps a disk to the host, it is identified by UIDs, like SCSI UIDs as we know. But in terms of NVMe, those namespaces are denoted by NGUID. So like this is other thing related to admins, like if they want to identify, my drive is NVMe, now it is SCSI, so they can relate between these two UIDs. So, so these were the steps like how the protocol stack is built upon. So as we have already gone through many of these things, so basically NVMe supports over RDMA thing or non-RDMA thing. When we talk about RDMA things, it is done by Rocky, IOP, or InfiniBand, which has been covered in many slides earlier. So this NVMe over Ethernet RDMA, they are going to 25, 50 gig, 100 gig, 200 gig solutions. So like they are generating lot of IOs and lot of throughput. So basically the workload which we are seeing today, for example, high performance computing, AI, and other things which generate lot of IO can get benefited out of it. And when we talk about this NVMe over InfiniBand, like this was earlier adopted, and it was, like it's one of the fastest protocol. So like it was used in, and it is getting used in AI and HPC environment, which requires processing at real time, and they have to get input of large IO. So like these are the use cases. NVMe over TCP is recently added option to the spec, and we have covered this in the last slide also, like how easy it will be to deploy. NVMe over FC is the one that we are continuing with this slide. So FC, as I have already said, is one of the protocol which is already used by enterprise customer, and you have already seen how easy it is to deploy. And it coexists with SCSI-FCP, and it leverages FC fabrics, existing FC fabrics. And this is a diagram. So basically, like we have NVMe over fabric. So NVMe over fabric can be in NVMe over fiber channel, or it can be NVMe over RDMA. And for non-RDMA stuff, we have TCP. And then this is something SCSI-FCP, which is not using NVMe. So like these are all the stacks which cover all the protocols. This thing I've already covered, like how easy the NVMe-FC deployment is and how easy it is for customer to use it without any cost. Like if they are having generation 6 cards, they can easily do a software upgrade and it will work. Now the thing is, we developed, the NVMe-FC support, and at the very initial time, Mohit did performance like when it was working. And very clearly we were able to see differences, like very at the start, what are the differences in latency, what are the differences in response time, what are the differences in CPU utilization. So like you can see very easily, and you can tell the customers also how they will get benefited to it. So to talk more about it, I would like to hand over to Mohit.
Thank you, Saurabh. So, in the next slide, I will be talking about how was our setup, what we use for the testing, and the charts which will be showing the difference. So, this is something the setup looks like. So, all the charts which I am talking about are the performance benefit that host will get. We are not talking about the target side. We are talking about the initiator or the host side. So, in this, we had a Lenovo server which is on Intel 64 cores and 128 GB of RAM, and it had a Broadcom adapter 4x16, and there is a NVMe subsystem. There are two controllers in that on the target side, and all the numbers are taken with the help of VDBench, which is a open source Oracle software. Okay. So, these charts, in this slide I will show the charts which are a typical workload. We called it as a typical SCSI workload because most of the SCSI application run on the queue depth of 32. So, with queue depth 32, we have taken the number for FC, SCSI and NVMe. So, here you can see the IOPs and the response time both for FC, SCSI and NVMe are similar, but the host CPU utilization is different. So, in host CPU utilization, you can see the 50% of the drop in host CPU utilization with respect to NVMe. So, this is the major difference, and this comes because of the NVMe-FC efficient stack. So, the code in the NVMe-FC is very less as compared to the SCSI which we have on the host side or the Linux side. Going forward, in this we will see the IO intensive workload where the queue depth is of 512, and here you will see the major benefit. So, if you see here, the IOPs which were the host were able to do with SCSI is around 220K, and with NVMe you can do 400K of IOPs. So, this is the major difference, and the response time. So, response time for SCSI is is double of NVMe. So, in NVMe you can get the 400K IOPs in 1.2 milliseconds, while SCSI gives you 220K IOPs in 2 milliseconds or 2.2 milliseconds. And the host CPU utilization, so host CPU utilization is 1/5. So, when you will be running more IO intensive workloads, you will get more space for the applications to run on the host server. So, now you are able to get more IOPs with less CPU utilization on the host side, and now you can run the other applications. So, when you run some applications which are AI or machine learning applications, so they are very compute intensive and as well as data hungry. So, this will NVMe-FC will give the benefit of both. So, now you will get the data benefit as well and the CPU utilization. So, we use the VDBench. No, it's a block storage. So, we use 4K IOs, 4K IO size. So, 4K IO size with 70% read and 30% write. No, so VDBench generates a block workload. So, it's a tool which generates a workload. So, it's a standard tool used by storage for the benchmarking. So, that's what I am saying. So, we use the queue depth, varying queue depth is the one. So, so any application will come down to the queue depth, how much IOs it pumps at a particular time, that we called as a queue depth. So, we have taken all the numbers based on queue depth. So, the first chart was showing on queue depth 32 and this is queue depth 512. So, 512 commands are being pushed at the same time. Okay. So, in this slide, I will be talking about the varying queue depth. So, we have taken results from queue depth 1 to queue depth 4096 and how the performance changes. So, if you can see, till 32 or 64, both SCSI and NVMe will give you the similar IOPs and the response time. But CPU utilization changes. But after 64, the CPU utilization and the performance for NVMe changes a lot. So if you can see, the SCSI peaks out at around 220K IOPS at 64Q depth, and NVMe continues till 400K IOPS. So if your workloads is somewhere between 64K to 1024, then you will get the benefit at all the levels. If your workload is below 64Q depth, then you may not see that much difference in the response time, but the difference will be there in the CPU utilization. So this is the chart which summarizes which kind of workload will be benefited majorly. So workload which are more IO intensive will get more benefit with NVMe, and these workload are restricted by the target ports, because we have used only 4 target port for this workload and 4 initiator port. So if you have more target ports, same host can able to drive more IO. So when we did the for larger target port with 4 host ports, we were able to get more than 1 million IOPS, which was not possible with the SCSI. So this is the major benefit. So now in your single 2U server, you are able to get with a single adapter more than 1 million IOPS with the same number of ports, and that too with a less CPU utilization. So this is the major benefit you will get from NVMe-FC.
Okay.
So block size is of 4K. So all the numbers are taken on 4K block size. Latency is also on 4K. 4K of.
Is that answered your question?
So what are the value proposition and where you can see? So the benefited workloads, as I was saying, so traditional workload which are OLTP or databases or high performance workload will get the benefits, because in this case when you are having this kind of higher workload, people used to have the host clusters to get the better performance with the help of SCSI. With NVMe, you can now reduce the size of host cluster. So if there were 5 or 6 hosts in a single cluster, now you can get that performance in a 1 or 2 host. So that is the major benefit of the NVMe in the traditional workload. Newer workloads like IoT, MLDL and data analytics, they already are IO intensive. So you will get the benefit there as well. And cloud native workload, where you will have the multiple VMs, Dockers running. So you will be, your system will be generating lot of IOs, so that will also get benefited. So all of these workload majorly comes between the queue depth of 256 to 1024 or 2048, and where you will see where you have seen the major difference between the performance, which I have shown in the previous slide.
Yeah, so thank you, Mohit. So like what Mohit did is like he mapped his performance reading with the workload. I just want to summarize this slide and reach to a conclusion. So like first I would talk about NVMe-F server benefits. So like how customer will benefit from adopting this thing. So the first thing is higher IOPS per CPU cores. He will see more IOPS per CPU core, reduce CPU utilization. So like this is very one of the major customer benefit that he will see. So when we say about reduced CPU utilization, we can think in 2 aspects. Like one is like if CPU is not utilizing much for that application, you can add new application and you can add more number of application in the same server. So like this is what cloud environment does. Like it tries to pack everything in a in a single server. So like this is something is a major benefit for the customer, and Mohit has showed very clearly how the CPU utilization goes down when we talk about NVMe-FC. This is scalable and consistent performance. So like when you see the graph, like it's straight, and you can scale this. Like when I talked about this NVMe-FC protocol, I already told you that there are association, there are connection. When a login happens, the initiator says, I am capable of doing 1000 queues I can create. I can run 1000 IOs on it. The host side will say, I am not able to do it. I am only doing 500 queues I can create. I can only run 100 commands, no problem. For this particular time, this will be the scalability thing. But in the future, suppose we are able to create thousands of queues, what we have to do, we just have to upgrade the software. We have to, increase the memory which is required for each IOs, and this can be easily scaled. And this is a consistent performance, and when we talk about consistency, fiber channel is something which gives you a very good, consistent, and reliable performance. So like this is, an add-on on this. Reduced response time. When we talk about, reduced response times, so like there are many workloads which demands very reduced response time. When we talk about high performance computing, so what happens is large amount of data needs to be pushed to the channel, and that needs to be computed very quickly and analyzed in real time. So like this is what the customer will benefit. User space programming model. So like the software that we developed mostly, it was written in user space only, and the server side can write, and like these are easy to extend. These are easy to extend, and lot of RAS can be pushed into it. Reduce port density. So by reduced port density, we mean we don't have to have lot of ports now in the server. By less amount of ports, we can generate the same number of IOPs or throughput, right? So this is also a cost factor. Like it was asked how much more capital is required. We are saying the one that you are spending, you can reduce that also. What I mean is you can reduce down your CPU numbers, you can reduce down your port density also, and you will get the same performance. So like this is one of the major benefit that customer will see. When we talk about FC benefits, uses existing FC fabric with 0 changes. I have already told, like what is required is a generation 6 adapter which has capability of both SCSI and NVMe-FC. So like with 0 changes, you can use it. Riding on back of FCP stability. So like FC is something very reliable. It has, concept of P2B credit, and it knows how to handle congestion, everything in the infrastructure. Coexistence of SCSI and NVMe-FC. I've already told you, through the same port and through the same channel, both SCSI and NVMe-FC is working, and they are doing fine. If you want to segregate it, you can have logical links by creating NP-IV WWPNs also. Easy migration from SCSI to NVMe. I've already told you, how customer can easily use the same channel. Like I have told things like SCSI and NVMe drives when exported to LUNs, they have different identifiers for them. And like this will what admin will see, and most of the thing, like it will be very easy for, migrate from SCSI to NVMe. So like the customer can start using it very quickly. So now talks about NVMe-F controller benefits. So when we are saying about NVMe-F controller benefits, we are talking about the target side. So when we talk about target side, like these are the systems which will provide the storage. So effective utilization of multiple cores. What do I mean on this? So we have seen that we can create lot of queues, and lot of queues will pump IOs. So suppose we have n number of cores, we can efficiently divide all those queues on those CPUs, and like everything will be, each core will be utilized. Earlier what used to happen is, suppose you have 8 cores, right? You have 8 cores, you have 2 adapters, 4x16 you can take. So what was happening is, like suppose you have 8 core and only 4 ports. Only 2 ports are, only 4 ports are mapped to it, and you don't want to have locking and all, you were not utilizing the other 4 cores. So now it is not the case. You can use all the cores, you can spread it widely, and there will be efficient utilization of, multiple cores. IOPs improvement, like more IOPs will be generated for that target system. Increased port efficiency, like each IOPs will generate more IOPs than earlier. reduce port density. So by this I mean the same thing, that you do not need to extend. Like suppose currently you are using 16 number of ports. It is sufficient for NVMe. Like it can use these 16 ports. You don't need to make it to 32 ports to have more IOPs. Like these can be used and more IOPs can be pumped. This is a scalable design, already told you by the number of queues and number of deep queues, and each deep queues having lot of commands inside it. So when we talked about benefited workload, I have already mentioned high performance workload, OLTP and databases. So like in these OLTP database, there are lot of queries, like there are a lot of user and each user wants response time quickly. So like this is the workload that NVMe F provides. New workload, data analytics, IoT, MLDL. As I've already said, that there is a need to process large amount of data, compute it in real time, and give it back to the user. So like these are the workloads which NVMe F can easily process and get the response back to the customer. Cloud native workloads, Docker, containers, VM. So I've already told you that in cloud environment, there is a need for packing up. There is a need for packing up lot of application in the same server. There is a demand, like lot of users are asking for compute thing, lot of users are asking for storage. So you have to respond to lot of users at the same time. You should pack everything. So like this is what NVMe-F is providing. It is providing reduced CPU utilization. With the same number of CPU, you can add more application and the user will see less response time. So like these are the workloads which will get benefited. Customer benefit, already mentioned, no additional capital investment is required. Low risk and ease of migration. So like very easily, customer can move from SCSI to NVMe. Improved utilization of most of the things. Like if you see CPU utilization is better, then port utilization is better, memory utilization is better. So all the resources are effectively used. Vertical scaling. So now you don't want to buy new servers. Like for the same server, it can give better performance. So you can have this vertical scaling. Application server consolidation, as already I have told, that more number of application can be accommodated in the same server, and customer can use. So like you can see, like this is something which customer wants very urgently, and because it will not incur much cost, and like this was something it has been in the market, and we are improving it also. And lot of data center work on fiber channel protocol. So like easily they can upgrade it with zero cost and get all of those benefits. So so I think like this is the summary of what we wanted to tell you. So thank you very much. Thank you.